Hello everyone! Today we are going to finish Chapter 9 and we will discuss Sections 2 and 3. So last time we talked about valence bond theory. Today we're going to talk about molecular orbital theory, and at the end I'm going to have a summary of both of these types of bonding theories. So molecular orbital theory, what is that? Well, MO theory is, the theme is that we view a molecule as a collection of nuclei surrounded by delocalized molecular orbitals. So that means all of the electrons of the molecule are spread out over the whole molecule. They don't just belong to a particular atom. Also, we should remember that atomic orbitals are wave functions, and we can sum them to obtain molecular wave functions. And just like valence bond theory, the number of molecular orbitals is equal to the number of atomic orbitals that we started with. But because they're waves, we can have wave functions that reinforce each other. And that means we have a bonding molecular orbital, or a region of high electron density between the nuclei. If the wave functions cancel, we have an anti-bonding molecular orbital. And that means there's a node of 0 electron density between the nuclei, and means that we will not find an electron there. So we can illustrate this kind of like we would with light waves. So we just have an analogy here. So here are the two nuclei shown as these black dots right here. And if we have a wave function right here, an atomic wave function, and they reinforce each other, that's called constructive interference. So the waves are in phase, we add the two wave functions together, and what we get in between them is a high probability of finding an electron between those two nuclei. So that would be a bonding molecular orbital. We can also have the possibility that the waves cancel, and what happens here is right in between these nuclei, our probability of finding an electron is 0. So we have a node. So the waves are out of phase, and the amplitudes of the wave functions are subtracted. So we have a low probability of finding an electron between each of these nuclei. We have a probability of finding an electron here and here, but not in between them. So that would be an anti-bonding molecular orbital. So the way that this works is we start with H2, our simplest molecule, just like we did with valence bond theory the other day. So let's take two isolated hydrogen atoms, and they both have a nucleus and one electron, which is demonstrated by this spherical cloud. And if we add these together, we get a bonding molecular orbital. We'll call that sigma 1s. And this is the addition of both of these atomic orbitals. But we also get an anti-bonding molecular orbital. We're going to call that sigma star 1s. So you can see there's a node in between, and there's no probability that we will find an electron in between those two nuclei. So we took two hydrogen atomic orbitals. We took one here and one here. So two atomic orbitals gives me two molecular orbitals, a sigma 1s and a sigma star 1s. We should note that the bonding molecular orbital is lower in energy than the atomic orbitals from which it came, because the electrons are spread out over a larger distance. But for the the anti-bonding molecular orbital, the energy is higher than the atomic orbitals that combine to form them. So we can show that here too. So an in-phase bonding molecular orbital, there's a high probability of finding an electron between them. So that's demonstrated by the sigma 1s diagram right here. Again, it's lower in energy because the electron density is spread out over a larger area than it would be if you had the two atomic orbitals. Up here, this is the anti-bonding molecular orbital. So this is out of phase. So low probability of finding an electron. The density is higher. And whereas there's an attractive force going on here with the bonding molecular orbital, with the anti-bonding molecular orbital, you can see that the nuclei are being pushed apart. So that's why we call it anti-bonding. And it's a sigma star 1s. So the general rules are that the number of molecular orbitals that we get is equal to the number of the occupied atomic orbitals that we started with. One orbital holds at most 2 electrons with opposite spins. That's the Pauli exclusion principle. We've seen that before. Orbitals are filled in order of increasing energy according to the Aufbau principle. Orbitals of equal energy are half filled. with spins parallel before any is completely filled. That's Hund's rule. And we are going to redefine bond order. So bond order, we'll use this equation. It's 1/2 the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals. So let's do an example. Okay, so we're going to draw an energy level, a molecular orbital energy level diagram for H2, the simplest molecule. So we start out with two atomic orbitals of hydrogen, and they each have one electron in each of these 1s atomic orbitals. So our electron configuration for hydrogen, of course, is 1s1. So what we're going to do now is we're going to mix those two, and now we are left with two molecular orbitals, bonding of lower energy, anti-bonding of higher energy. So the bonding orbital is sigma 1s, the anti-bonding is sigma star 1s. So now we have two electrons. We're going to put two electrons in the sigma 1s. We start there because the energy is lower, and we can only put two in this bonding molecular orbital, and we are finished because two electrons is all we have. So we can calculate the bond order, so it's 1/2 times 2 minus 0, so we have 2 electrons in the bonding molecular orbital and 0 in the non-bonding, so 1/2 times 2 is 1. So we have a single bond between the two hydrogen atoms. And valence bond theory would have predicted that as well. Now, one of the things we can do is we can write an electron configuration for this molecular orbital of H2. So we can say sigma 1s, because that's the orbital, and we put parentheses around it, and we write a superscript 2, because we have 2 electrons in that sigma 1s molecular orbital. Okay, so let's go on. Let's do some other examples. Now we're going to do maybe some odd examples. Maybe you were not used to thinking of diatomic helium, and there's a reason for that. Or we can write He2 plus. So if I take 2 helium atoms and try and put them together, but if they're positively charged, that means instead of having 1s2, 1s2, one of these is missing an electron because this is a positively charged ion. So I have the atomic orbital of helium, which is 1s2, and the atomic orbital of He plus, which is 1s1. So I'm going to do the same thing. I'm going to take my 2 atomic orbitals and I'm going to mix them. And I form a bonding molecular orbital and an anti-bonding molecular orbital. And this is sigma 1s, that's sigma star 1s. And now I have 3 electrons to put in these orbitals. So I have 1, 2, 3. So I paired these up first. I can only have 2 electrons in an orbital, and once it's full, I go up to the higher energy. So I can write the electron configuration of He2 plus. So it's sigma 1s superscript 2, because I have 2 electrons in the sigma 1s, and I have the sigma star 1s, and I have 1 electron in that orbital. And I can also calculate the bond order. So an He2 plus bond order is 1/2 times 2, that's the number of electrons in a bonding orbital, minus 1, which is the number of electrons in the anti-bonding orbital, and I get 1/2. So the bond between them isn't very strong, but it is real. We can actually make these He2 plus ions. What about diatomic helium? Well, I'm not going to do the whole thing like I did before, but this is, if we have helium, we have 1s2 and another 1s2, and here we have 4 electrons. So we put 2 electrons in the sigma 1s, 2 electrons in the sigma star 1s, and we find when we do that, that if we calculate the bond order, it's 1/2 times 2, that's the number of electrons in the bonding molecular orbital, minus 2, the number of electrons in the anti-bonding molecular orbital, and we get 0. So what that means is He2 does not exist. So we would have predicted that before. Helium is a noble gas, and it doesn't like to form diatomic molecules. So we would have predicted that for valence bond theory, and molecular orbital theory predicts that as well. There is no such thing as He2. We can draw this energy level diagram and show that He2 does not exist. So what's this bond order? Okay, so in molecular orbital theory, the stability of a covalent bond is related to its bond order. So any bond order greater than 0 indicates a stable interaction. That's why I was able to say that the He2 plus, that there was some kind of interaction between them because the bond order was 1/2. It was greater than 0. So a bond order of 1 is a single bond. So the bond order for the 2 hydrogen atoms, that was 1. So there's a single bond between the 2 hydrogen atoms. A bond order of 2 is a double bond, and a bond order of 3 is a triple bond. So we can have molecules with odd numbers of electrons. We can have bond orders of 1/2 or 3/2 or 5/2. Just use that equation and we can figure out the bond order. And again, the greater the bond order, the greater the strength of the interaction between those two atoms. So again, hydrogen had a bond order of 1, and helium, He2, did not have a bond order at all. Its bond order was 0, which means no bond forms. So the greater the bond order, the stronger the bond. If the bond order is 0, that means no bond forms between those two atoms. This is a sample problem in another textbook I used before we adopted the current textbook, but it's similar to the example problems given in example 4 in your textbook. So here we're asked to use MO diagrams to predict whether H2 plus and H2 minus exist. So we'll do that by determining their bond orders and electron configurations. So we'll use H2 as a model and we'll figure out how many electrons we put in the bonding and the antibonding orbitals, and then we can use that equation to find the bond order. Okay, so we have an atomic orbital of hydrogen. So if this is H2 plus, that means we have 1 electron in one of the hydrogens, but then we've taken away another electron, because it's a positively charged ion. So we only have 1 electron combined. So let's mix these to form an MO, a molecular orbital of H2 plus. So we mix them and we get our sigma 1s and our sigma star 1s, and then we just take the single electron we have and we put it in our sigma 1s orbital. So the bond order is 1/2 times 1, because that's the number of electrons in the bonding molecular orbital, minus 0 is 1/2. So H2 plus does exist. That's not particularly stable, but it does exist. Its bond order is not 0. So there is somewhat of an interaction between H2, two hydrogens when you pull apart one of their electrons. So, and the configuration would be sigma 1s1, because we have this sigma 1s electron configuration and we only have 1 electron in it. What about the second part of the problem, H2 minus? Well, here we have a hydrogen has 1 electron, another hydrogen has 1 electron, but we have an extra electron because it's H2 minus. So if we do the same thing where we take these 1s atomic orbitals and mix them to form the sigma 1s and the sigma star 1s orbitals, then we've got 3 electrons. So we put 1 here, 1 here, and 1 here. And the bond order then is 1/2 times 2. We have 2 electrons in the bonding orbital minus 1. We have 1 electron in the non-bonding orbital, so it's 1/2. So H2 minus does exist. Again, not very strong, but it's not 0. So the electron configuration for the H2 minus species then is sigma 1s2, sigma star 1s1. Okay, so that's the first period. If we look at the periodic table, we have in the first period only hydrogen and helium. So let's go to the second period and let's look at lithium 2 and beryllium. Okay, so we have our lithium, our diatomic lithium, now lithium's electron configuration is 1s2, 2s1, but the 1s2 electrons, those are core electrons. Those are the electrons that are the same as the electron configuration of helium. So I'm just going to do 2s. I'm ignoring the 1s's because they're full. So I'm just going to the valence electrons. Lithium has only 1 valence electron in its 2s orbital. So we have a 2s1 here and a 2s1 here. So we mix them and we get sigma 2s and sigma star 2s. So again, we had only 2 electrons, so we put 2 electrons here. So we have This would be the whole electron configuration if we started from the beginning. It would be sigma 1s2, sigma star 1s2, sigma 2s2. But I don't think it's necessary to write out the whole thing. This is how I want you to do it. I'd want you to write just helium and then what's beyond the helium, just like we did in chapter 7 when we were looking at electron configurations for atoms. So this is sigma 2s2. So we have the sigma 2s orbital with 2 electrons in that orbital. And we calculate the bond order. So it's 1/2 times we have 2 electrons in the bonding orbital minus no electrons in the non-bonding orbital. So that is 2 minus 0 is 2 times 1/2 is 1. So we do in fact have a bond between lithium. So Li2 diatomic lithium can in fact form. What about beryllium? Let's look at beryllium. So if we continue on the periodic table. So beryllium's electron configuration is 1s2, 2s2. So again, we're ignoring the 1s2 because those are core electrons. We're just looking at the 2s2 because those are valence electrons. So let's take these and mix them. So we have sigma 2s and sigma star 2s. We had 4 electrons to place in these, 2 in the sigma 2s, 2 in the sigma star 2s. And then this is how we can write the electron configuration. We can write helium, then sigma 2s2, sigma star 2s2. And when we calculate the bond order, we find if that we have 2 electrons in the bonding orbital and 2 electrons in the non-bonding orbital, we get a bond order of 0. So that means that Be2 does not exist. So we can draw these molecular orbitals to show that Be2 does not exist. So we can notice that the S-block diatomics, the lithium and the beryllium, repeated the pattern of period 1, where we had hydrogen and helium. So like hydrogen, H2, Li2 can form a stable diatomic molecule with bond order of 1. Now that is maybe not our experience. So lithium at room temperature is a solid metal. So diatomic molecules form only at high temperatures and low pressures. But we can actually go into that kind of environment in the lab and we can actually make Li2. But like He2, Be2 is predicted to have a bond order of 0. So that means we never see Be2. Not under any kind of circumstances would 2 berylliums come together to form a diatomic molecule. Okay, let's keep going. So the next one is going to be boron, but now we are adding electrons to p orbitals. So we're in the 2p part of the periodic table. So if we mix 2p orbitals, we're going to get 2 types of molecular orbitals. So remember, with the s's, we just have spheres. With the p's, we have dumbbells, and we have 3 of them because we have 3 different orientations of these dumbbells. So sometimes these dumbbells can overlap end to end, which means the orbitals are form along an internuclear axis, and here we form sigma 2p and sigma star 2p. So you might remember from valence bond theory that when we form sigma bonds, that was end to end overlap. We can also have side-to-side overlap. So orbitals form perpendicular to the internuclear axis, and they combine to form pairs of pi 2p and pi star 2p, and we get 2 of those. So we have 1 set of end-to-end and 2 sets of side-to-side. Okay, what does that look like? Well, it looks like this. Okay, say I take 2, I'm going to start with boron in a second here, but say I take 2 atoms and both of them have p sub x orbitals. So there's one nucleus and there's the other one, and say that they're going to overlap end to end. So we're going to do the addition and the subtraction. And when we do the addition, we get this kind of funny looking thing right here. But this is a bonding molecular orbital. So remember the shapes, all the shapes are regions of electron density where you're most likely going to find an electron. So we can see we have a pretty high probability between, again, these dots are the nuclei. We have a pretty high probability that we're going to have electron density between those 2 nuclei. So this is sigma 2p. So again, this is a lower energy because the electrons are spread out over a larger area. But this is the sigma star 2p. So again, when you subtract these 2, this is what you get, and you get a node in between. Okay, so we have one pair of the p orbitals interacts end to end. We got two pairs left. This diagram only shows the p sub y. But the p sub y is up and down. Remember, the p sub x is going to be at another orientation. But we can do the same thing where we can do an addition and subtraction. So if we add the two p sub y's, our bonding, so we get a pi 2p molecular orbital. So this is the addition. Its energy is lower. The overlap is side to side. So we, again, here are the nuclei. Between these nuclei, we have this high region of probability that we're going to find an electron. But if we subtract, we get these shapes and we get a node. So this is a pi star 2p. It's an antibonding molecular orbital, so the probability of finding an electron there is very low. So I wish I had another picture that showed the p sub z, but in your mind, draw another p sub z, also doing the side to side overlap. So p sub y is the only one being shown here. P sub c does the same thing, but it just does that in a different orientation. So we have p orbitals, we have 3 of them. One pair of p orbitals interacts end to end. 2 pairs of p orbitals interact side to side. So the p orbitals that interact end to end form sigma bonding and sigma star antibonding molecular orbitals. The p orbitals that interact side to side form pi 2p and pi star 2p bonding and antibonding molecular orbitals, respectively. Okay, so what does that look like? Well, what that means is that we can have a diagram that looks like this. So here are our atomic orbitals, and we mix to form the molecular orbitals. So here's a sigma 2s and the sigma star 2s. So we have 2 atomic orbitals shown in white, and then the 2 molecular orbitals that they form shown in gray. So here for the 2p, we have 6 atomic orbitals. We have 3 here and 3 here. So if we're going to mix 6, we're going to get 6. 1, 2, 3, 4, 5, 6. So we have the sigma 2p and the pi 2p, and then we have pi star 2p and the sigma star 2p. So this is listed in order of energies, with the bonding molecular orbitals being lower in energy and the anti-bonding molecular orbitals being higher in energy. So another wrinkle here is that these are the molecular orbital levels in these indicated energies you get for oxygen, fluorine, and neon. So what we say here is that the 2s and the 2p orbitals didn't mix. But what happens if I look at boron, carbon, and nitrogen? Remember, those diatomic molecules are going to be larger. Remember, when you go across a period, the atoms and their molecules are going to get smaller. So, so this is what the smaller diatomics look like. These are the larger ones. So what you can see here is that when we have some what we call 2s, 2p mixing, we get something that looks like this. So we have a decreased energy in the sigma 2s and the sigma star 2s. So see how the sigma 2s is lower in energy here, and the sigma star 2s is also lower in energy. And if you look over here, see how this was sigma 2p and this was pi 2p. Here it's pi 2p and sigma 2p. So that's really the only thing we have to worry about. We don't have to worry about these relative energies, but we do have to worry about knowing that are we at boron, carbon, and nitrogen? And if that's true, the pi 2p's have a lower energy than the sigma 2p. But for O2, F2, and Ne2, the sigma 2p has the lower energy than the pi 2p. So this is a diagram from our textbook. So here they show the B2, C2, and N2, and they show this really nice colorful picture right here where we can nicely see the triple bond between the N2 molecule. So again, and they show the whole thing. They show 1s, 2s, and 2p. So again, 1s, 2s, and the 2p. So here we show the pi 2p orbitals are lower in energy than the sigma 2p, and that's true for boron, carbon, and nitrogen. So this is a diagram from another textbook that I have, but I like it because it shows exactly what's going on with each of these elements as I progress along period 2. So this is boron, carbon, nitrogen, oxygen, fluorine, and neon. And we see that for the boron, carbon, and nitrogen diatomics, we have this 2s2p mixing, which means that we have the 2p orbitals have a lower energy the pi 2p orbitals have a lower free energy than the sigma 2p's. Here we don't have the mixing, so that means that we have the sigma 2p's have a lower energy than the pi 2p's. There's some other interesting things here, but we will return to in a minute. But I just wanted to show you that we do get some mixing, which changes the order of the energy of these bonding molecular orbitals. So in period 2, it's still true the molecular orbitals from the p atomic orbitals are always higher in energy than the s's. So when we draw these, we always draw s at the bottom, and then we progress to p. So that's going to be true. Antibonding are also higher energy than bonding. That's still going to be true. The end-to-end orbitals, it turns out they can interact more strongly with each other than the side-to-side. And that makes sense too, because they just have more space, more kind of areas of interaction end-to-end than you do side-to-side. So that means that in general, the sigma 2p molecular orbital is lower in energy than the pi 2p. But we do have to keep in mind these relative positions because it's different from the boron, carbon, and nitrogen diatomics because you get this mixing. Then for oxygen, fluorine, and neon, you get the expected results without the mixing. Okay, so the next thing we want to talk about is diagmagnetism and paramagnetism, because I went back to chapter 7 because we've talked about this before. We said that substances with no unpaired electrons are weakly repelled by a magnetic field, and we call this diagmagnetism. And substances that had no unpaired electrons were considered to be diamagnetic. But if you have one or more unpaired electrons, then you're attracted to a magnetic field. And the more unpaired electrons you have, the stronger the force of the attraction. So this is called paramagnetism. So if I have my electromagnet off here, then and here's my balance right here, and I have a sample in a sealed glass tube. But if I turn the electromagnetic on, then the substance that's in the tube is going to be attracted to the magnet, so it tips the balance over here, so we can see that attraction. All right, so why do we bring this up now? Well, that's because if you look at diatomic oxygen, if I were to ask you to draw a Lewis electron dot structure for oxygen, you draw like this. So oxygen has 6 valence electrons, so you draw this 2, 4, 6, 8, 10, 12. So each oxygen contributing 6 valence electrons, and you draw a nice double bond between them and 2 unpaired electrons. And then if I asked you if it was diamagnetic or paramagnetic, you would tell me it's diamagnetic because there are no unpaired electrons. But if we go into the lab, oxygen is paramagnetic. So maybe we should draw it like this, where we draw a single bond in between and we have these unpaired electrons. So valence bond theory, like we would never draw a structure that looks like this. And valence bond theory or Vesper theory, or the way I taught you to do Lewis structures. But if I go back to this diagram, and here's O2, and remember we don't have 2s2p mixing here. If we fill up all of our electrons, you can see that we have 2 unpaired electrons right here in this pi star 2p orbital. So in fact, we do in fact have 2 unpaired electrons. Our Lewis structure doesn't make it look like that, but that's what it looks like according to molecular orbital theory, which is sort of a paradox because if you look at the oxygen molecule, its short bond distance and its high bond dissociation energy really is in agreement with this double bond. And we often draw oxygen like this, but we do have to account for the paramagnetism. And molecular orbital theory is the only way we can do that. So this is our chapter opener. So this shows the paramagnetic properties of oxygen. So this is liquid oxygen, and if you pour it between the poles of a magnet, you'll see that the oxygen is attracted to the magnet. So I'm going to go on YouTube and show you this video that I found of two students who will demonstrate this for us.
Frostbite Theater presents Gold Guts, no baloney.
Just science. Hi, I'm Joanna.
And I'm Steve.
And this is a test tube of liquid nitrogen.
And this is a test tube of liquid oxygen.
Let's see what happens when we pour the liquids past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diagmagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So, when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
All right, so if we look at our molecular orbital diagram for nitrogen, you'll see that, as Joanne says, that all the electrons are paired. So that molecule demonstrates diamagnetism, but we can see that oxygen is clearly paramagnetic. It really is attracted to these two poles. So molecular orbital theory is really the only theory that can explain how that works. So what are the advantages of molecular orbital theory? Why do we introduce this after spending so much time talking about valence bond theory the other day? Well, it does correctly predict magnetic properties of molecules. Molecules with paired spins, such as nitrogen, as you saw in the video, are diamagnetic and they're not attracted to magnets. But molecules with unpaired spins, like oxygen, are paramagnetic and they are attracted to magnets. And molecular orbital theory, unlike valence bond theory, does predict that oxygen does have these two electrons with unpaired spins. The other thing is that MO theory deals in a more natural way with molecules that require resonance structures. So if you use MO theory, you just have one structure. You don't have to draw all those many structures that we've been drawing for the last couple weeks because one structure wasn't sufficient to describe a molecule that exhibits resonance. I wanted to draw the MO diagram for NO because I wanted to do something that wasn't just two atoms that were the same. So again, I can draw Lewis structures for NO. NO is one of those unpaired electrons because nitrogen has 5 valence electrons and oxygen has 6. So my Lewis structure is going to have 11 valence electrons. So we have 2, 4, 6, 8, 10, 11. So I can either put the lone electron on the nitrogen, or I can put it on the oxygen. And probably we would draw it like this because if we calculated the formal charge, drawing it this way gives us non-zero formal charges on the NO, whereas this way we have formal charges. But it's a lot easier, maybe I don't know, maybe a more effective way to describe the bonding in NO with a molecular orbital diagram. So what we do is we take an atomic orbital of nitrogen. So nitrogen has 5 valence electrons. So we have 2s2, 2p5, sorry, 2p3. So 1, 2, 3, 4, 5. We have 5 valence electrons, and we have 2 atomic orbitals, a 2s orbital and a 2p orbital of nitrogen. And then for oxygen, oxygen is 2s2, 2p4. So we have 1, 2, 3, 4, 5, 6 valence electrons. So if we mix them, we're going to get something that looks like this. So if we look down here with the 2 s's, so we mix the 2 s's, so we get a sigma 2s and a sigma star 2s. We have 1, 2, 3, 4 electrons in the atomic orbital. So we've got 1, 2, 3, 4. We have 2 in the sigma 2s and 2 in the sigma star 2s. And then over here, we've got 1, 2, 3 electrons here, and 1, 2, 3, 4. So we have 3 plus 4. We have 7 electrons to place in these molecular orbitals. So we put them 1, 2, 3, 4. Not in that order. I would actually put them in this order. I would put 1, 2, 3, 4, 5, 6, 7. So we have 6 electrons in bonding molecular orbitals and 1 in a non-bonding molecular orbital. So the other thing that we pointed out is that the lowest energy, that should say pi bonding instead of p bonding. So the lowest energy pi bonding molecular orbitals in benzene and ozone are shown in this picture right here. So I didn't draw a molecular orbital diagram for this because it's kind of complicated. But if you remember benzene in our book, it showed a hexagon with alternating single and double bonds. And you had to write 2 of those because who is to say which were the alternating double bonds are? Well, benzene doesn't really look like that. Really, it looks like a ring of electrons. So again, in the MO visualization of how this works, all of the electrons belong to the entire molecule. They don't just belong to some atom. So we have this ring of these unhybridized p orbitals that describe the electrons in benzene. And then ozone we did draw, and again we drew an oxygen in the middle, 1 single bond, 1 double bond, and again that didn't work. Really what we have is we have 3 oxygens bonded together, and their bond strengths and bond lengths are the same. And here we can visualize that we have this end-to-end unhybridized p orbitals overlapping to form these regions of electron density between the oxygens in the ozone molecule. All right, so how should we reconcile this? How can we summarize this? Okay, well, let's remember valence bond theory. That provides a qualitative visual picture of molecular structure and bonding. We look at the central atom, and the central atom hybridizes, but the other orbitals didn't. So we visualize the bonds formed as overlapping orbitals, but it was only the central atom that hybridized. The number of hybrid orbitals is equal to the number of the atomic orbitals that we combined. We have unused orbitals that might be empty. They might participate in pi bonds, or they might explain why a particular molecule is unusually reactive because it might want to fill those orbitals. Molecular orbital theory, on the other hand, they combine to form molecular orbitals that belong to the molecule as a whole, and it's useful describing molecules in higher energy excited states. So if you're trying to explain why molecules react the way we do, which we have not just tried to do in this chapter, but later in your career you will, MO theory can help us out in that regard. It explains why some compounds have specific colors. That valence bond theory won't do that for us. And for a few molecules like NO and O2, the bonding can be accurately described only by molecular orbital theory. Valence bond theory will not do that for us. So I hope you enjoyed our explanation of molecular orbital theory. Please do these problems for homework, and I will see you next time.